Welcome to part 1 of the lesson on section 3.9 related rates. In this lesson, you'll learn how to solve related rates problems involving right triangles, area, and/or volume. In a related rates problem, we're usually asked to solve for a rate of change given how other rates of change are related to various quantities in the problem. In our first example, suppose you're blowing a bubble with bubble gum and the rate at which you can blow air into the bubble is 3 cubic inches per second. This question has a part A and a part B. We'll look at part B in a later slide. Part A asks us to find the rate at which the volume increases with respect to the radius when the radius is 1 inch and when the radius is 3 inches. Our first step is to assign variables and translate the given information and what we're asked to find into symbols. The 3 cubic inches per second is a change in volume over change in time, so we should call that dV dt. In part A, the rate at which the volume increases with respect to the radius is change in volume over change in radius, or dV dr. And we're going to find that at the instant when the radius is 1 inch. A diagram is probably not necessary for this one, so we'll skip that step. Next, I need to write an equation that shows how the variables are related. Time doesn't come into play in part A. We'll deal with that in part B. In part A, we need to show a relationship between volume and radius. Let's assume the bubble is spherical, so its volume is 4/3 pi r cubed. Next, we'll use implicit differentiation to show how the rates are related. Remember that in Leibniz notation, dV dr means that v is our dependent variable and r is the independent variable. So when we take the derivative of v, we need to use the chain rule and include a dV dr. But the derivative of 4/3 pi r cubed will just be 4 pi r squared. You might not be that surprised by the results. We solved a problem during part 1 of this unit that dealt with change in the volume of a sphere in relation to a change in radius. Now, to find dV dr, substitute the value of r into the equation. For the second part of A, we'll do the same thing with r as 3 inches. In part B of the same problem, we're asked to find how fast the radius increases with respect to time when the radius is 1 inch and 3 inches. Again, let's start by assigning variables to the given information and what we're asked to find. From the last slide, we were given that dV dt is 3 cubic inches per second. The radius increasing with respect to time is change in radius over change in time, or dr dt, and we want to find this at the instant when the radius is 1 or 3 inches. Next, we write an equation relating the variables in some way. So we'll use the equation for the volume of the sphere again. Notice that time is still not part of the equation. Don't worry, you'll see how to deal with that in the next step. In our implicit differentiation step, we need to find dr dt. dr dt indicates that t is the input variable, so when we take the derivative, both the v and the r will require the chain rule. So notice we have a dV dt and a dr dt. Once again, we substitute numbers for as many variables as we can in order to solve the equation for dr dt. Here's what we get when r equals 1 and when r equals 3. In our second example, an airplane is flying on a flight path that will take it directly over a radar tracking station, as shown in the diagram. If s, the direct distance from the plane to the station, is decreasing at a rate of 400 miles per hour when x is 10 miles, what's the speed of the plane? Start by assigning variables. Before we do that, I want to point out the 6-mile altitude labeled in the diagram. As it's modeled here, you should avoid labeling your diagrams with any numeric values that do not remain constant throughout the problem. The 6 miles labeled into this diagram indicates that the altitude of the plane remains fixed at 6 miles throughout the problem. X equals 10 miles only at a particular instant in time, so it should not be labeled into the diagram. Anyway, back to assigning variables. The speed of the plane is determined by the change in distance x over the change in time. So that's dx dt. S is decreasing at 400 miles per hour, so that's a change in distance s over change in time. ds dt. Notice the negative to indicate that it's decreasing. Next, we write an equation showing a relationship between the variables. Since our diagram shows a right triangle, we can use the Pythagorean theorem to relate the distances. Most of our right triangle problems are either going to become the Pythagorean theorem or trig equations. In the implicit differentiation step, since we want dx dt, we'll treat t as the input variable. So both x and s will require the chain rule, and notice the dx dt and the ds dt in our resulting equation. Substituting, we know that x is 10 and ds dt is negative 400, but we don't have s. Can we find it? At this moment in time, the altitude is 6 and the horizontal distance is 10. Substituting that into the Pythagorean theorem gives us s equals the square root of 136. That gives us dx dt equals negative 40 times the square root of 136 miles per hour. This concludes part 1 of our lesson on section 3.9, related rates.